All right, so we're going to look at dilations, okay, today. And we're going to see what we can come up with here as far as like, page 577 is the section that we're going to be doing here.
We're like on 600.
577, I know, right? We backed up a little bit. I did things a little bit out of order from what the book is written in. Okay? So, the section here, again, is called dilations, right? The essential question is, how does a dilation transform a figure, right? So we've already seen some transformations. We've seen, like, translations. What's another word for translation? A slide, right? What about, we've also seen reflections, right? Sometimes flip, right? And we also seen rotations, which are the turns, right? So we've seen those three. Now, we studied those three separately because what do we kind of call those kind of transformations? They don't change the size of the shape. We call those what? Rigid motion transformations, because they maintain the same size and shape of our original figure. Okay? It just changes like the orientation or the position of it. A dilation, okay, is a dilation a rigid motion transformation? No, why not? Because the size and the sides change, exactly right. It changes the size and the sides, okay? So, a dilation is a transformation that can change the size of a polygon but leaves the shape unchanged. So the shape still stays the same shape, it's just smaller or bigger, okay? A dilation has a center of dilation and a scale factor, which together determine the position and size of the image of the figure after the dilation. Okay, so center of dilation, that's like what we're dilating from. We kind of zoom out, or not zoom out, but like get bigger from that, or get bigger, get smaller from that. And the scale factor is the actual like number you're multiplying each side by to then get these next sides. Okay, so I'm going to hold off on doing these angles right here, because that's just going to take some extra time with the protractor, but I do want to take a look at these sides, because I think that's more interesting, right? So if you guys want to go ahead, let's go ahead and measure some of these sides here, if you want to measure along with me. So it says AB, let's do that one first. So let's see here. So I measure from A to B. That looks to be almost exactly, I'd say 6 centimeters for that, yeah? From 6 and really? Okay, I'm going to say 6 for that one because that looks almost exactly 6. So, sorry, centimeters for sure there. Centimeters for sure. It's going to be more precise if we do the centimeters. So sorry guys. I know we're in America and we use inches here, but we're going to use centimeters. Okay. All right, let's do AC.
That's 4.
Okay, perfect. These are going to be really nice numbers here. And then BC is 3. Beautiful. That's great. Very nice. All right, so there's 6, 4, and 3. Those are really easy to measure. And then let's go to the A prime, B prime. Yeah, I got 3 for that as well. Okay, and then A prime, C prime. I would say 2 for that one. Very good. And then B prime, C prime.
1.5.
Yeah, 1.5. Very good call. Good calls there all around. Okay. Yes. So we'll get, yep, exactly right there, Matt. You're on the right track there, okay? So, angles here, I don't know if I really want to do these. Let's see, can I do them like quickly or easily here? So I'm going to go ahead and say, I'm going to do these real quick and just kind of eyeball them. So I'm going to say angle C is 120 degrees. Yeah, absolutely. If you guys want to see here, I thought if you want to see that. So, real quick, I'm going to review how to do the angle measures, right? So you put your so for example, I'm going to measure angle ACB. I'm going to put my protractor on one of the sides of the angle. It doesn't matter. You can put it on side AC or put it on BC. It doesn't matter. Since AC is already like flat towards me, I'm going to use AC. 577, Ramel. 577. Oh, it does not? Okay, well, let me check here then. So again, we line up our protractors on the base there and make sure then this vertical line matches up right to that point, the vertex there, point C. Okay, now I can see when I go to measure, what's my problem here when I go to measure my angle?
You don't know which
Yeah, my side is not long enough here. That's a problem. So what we can do is what? Make your side longer. Exactly right. And it's going to make it a little bit messier, but that's okay. Or punch it. Well, let me know if that works for you. Did it work there? You got the angle? All right. Well, let's also learn how to do it this way, too. Sorry, yes.
This is like the problem I had not yesterday, but...
Right, before?
Yeah, and you never came to me.
Okay. So, hang on a second. Okay. So again, we extend the side. And you're right. It is not exactly 120 degrees. Now, that's. I also heard a good question, though, too. Which set of numbers should we be using here? Should I be using the outside set or the inside set?
The outside.
Okay, the outside set. Can you tell me why there, Kyle?
Because it's going from, like, I don't know how to explain it, but it's going, like, to the right, so.
That's one, yep. So we can also think of it this way, guys. My angle that I put my protractor on the side right here, it should start at an angle of 0 and then count up. The other inner numbers are starting at like 180 and counting down, and that doesn't make sense. We want to count up. So we start counting up, and then I get to like this right here. So yeah, you can.
It's 116.5.
Is it 116.5?
Yeah.
Okay. I got like 117, or sorry. Yeah, I got 117. You got 118?
Yeah, I got 118.
Okay. So, again, I understand what you're trying to say, EK, but it's like we're all getting different answers, so how are you supposed to know which one's right? And so I get that.
I got 118.
That's a matter of, thank you. That's a matter that you don't have to worry about that for like a test or a quiz. I'm not going to like have you guys like say, oh, Ikeva says it's 117.5, Zara says 118, one of you's right, one of you's wrong. It's more like the numbers will be given to you to make it more obvious, you know what I mean?
So why are we practicing measurements?
Well, because I kind of want to at least show that they are, close to each other, and that the error is not because they're not similar, the error is just because of the protractor or just like the way we're using it or whatever, that's all. Just like with the compasses, sometimes we didn't get exactly the circle to fit inside or outside because, the compasses were great or whatever, so it's just more for the experience of it. It's just more for the experience. Okay, so I'm going to, just because I would like a nice number here, we'll go ahead and say that's 118 degrees, okay, for angle C. Okay, and then, I'm sorry. Thank you, Chardez. Right there, 118. And then we'll go ahead, and we're on page 588, or 577 there, Haley. Okay. Question? Okay, and then angle C, I'll go ahead and measure that one.
26.
All right, so what should angle C prime be? If these two things are similar, what should be the angle? It should be 118. And in fact, mine is pretty close to 118 there. If you look, I mean, if I mark it, there it is. It's pretty close. I'll go ahead and just say we'll go ahead and say it's 118. Okay. And then let's see here. I'll go ahead and measure angle A as well. So let's see. Let's do angle
I think
A.
it's 26.
All right. Mine looks like it's exactly 25.
How do you measure
Yeah, mine does too, but
So,
that's
all right, hang on a second,
Yeah,
real
they
quick,
have 20.
from the question there, EK's question. So, angle A, again, I'm going to measure from starting on this side again because it's like flat towards me. Put your protractor down on the normal kind of, right on the vertex there. And then we're going to use which set of numbers now?
So, inside.
The inside set, because again, our side of our angle starting here, the zero's here, we're going to count up, then we want to count up from 10, 20, and then, yeah, it looks like almost exactly 25 to me. So I'm going to say 25 for angle A.
It's actually 26.
Is it 26?
Yeah.
All right, well, I'm going to put 25 down just because I already have it written and I don't feel like scratching it out. But if you guys want to say 26, that's okay. And so then we can assume that angle A prime will also be 25, right? Okay, well, again, that's up to you guys if you want to keep it that way, okay? I'm going to say this. Now, we could measure angle B and B prime, but now that we have these two angles, how can I figure out what angle B's got to be? Not divide by 180. Subtract from 180. Yeah, okay. And I know what you knew what you meant, but okay. So I get 37 then is what the leftovers have to be. Okay. So now back to what Matt was saying a few minutes ago. He was talking about the ratios there. He actually was able to come up with a relationship here between the sides. So let's go ahead and set up these ratios. Notice here that they're very purposefully putting all of the images on top, and then all of the originals on the bottom. And that's something that we're going to be in the practice of when we talk about dilations. In dilations, we're going to have image measurements on top for the ratio, and then the originals on the bottom. Image over original, or image over pre-image, if you want to say that. Jaden, question for me?
How do you measure angle?
I just subtracted it from 180. I subtracted the other two angles from 180 to then get what angle B has to be. You know? So that's all. Okay, so let's do this. So A prime, B prime, that's 3. AB is 6. And then we want to try and get that to be a single number. Well, what is 3 divided by 6? 0.5. Yeah, 0.5. That's right. Okay. A prime over C prime, or A prime C prime is 2. AC is 4. What's 2 divided by 4? 2. It's that's 4 divided by 2. Yeah, 2 divided by 4 is 0.5. 1/2. And then B prime C prime is 1.5. And then BC is 3. So 1.5 divided by 3. Anybody? Yeah, it's going to be 0.5 again, okay? So look at this. All of our ratios are equal.
What if they're not equal?
If they're not equal, then it's not a dilation, and the triangles aren't similar, or the shapes aren't similar. They need to be equal. They need to be equal, right? That's what we talk about. Okay, so number 1, what do you notice about the corresponding sides of the figure? Well, what's true about those sides? Their ratios are all what? Equal, okay? So the ratios of corresponding sides are equal.
The corresponding sides of the figures?
Mm-hmm.
That's not equal.
The ratios of the ratios of corresponding
Oh,
sides
the ratio. Okay.
are equal. Yeah, that's why. Very key there, because you're right.
Yeah, but it says it doesn't say ratios, so what do you know about the corresponding sides of the figure?
Right, exactly. And so alone, the corresponding sides are not congruent. But if we put them in ratios, and because you see, they're kind of leading us through that point, because the very last step we did here was part C. We did ratios of the corresponding sides. Well, this is like, what do you notice about the corresponding sides? They're not equal, but what I noticed is that their ratios are equal.
Okay.
Yeah. All right. Okay. And then what do you notice about the corresponding angles? Okay. So yeah, they are congruent. Okay. And corresponding angles are congruent, which we know then guarantees these two triangles are similar. And if you want to use the symbol for congruent instead of the word congruent, that's fine too. Okay. if you want to use-
Corresponding what angle?
Oh, I'm sorry, I went off the page there, thank you. Corresponding angles are congruent. Okay.
If you were to put, like, for the ratios, if you were to put 4 over 2, would you get it wrong?
So, it depends on what you're trying to do. If you're trying to solve for sides, Jaden, like if you have like one ratio and then you want to use it to solve for another side or something, that's fine. The order doesn't matter. But if we're trying to find like scale factors, if we're trying to talk about dilations, you really want to get in the habit now, because we're talking about images and pre-images. Whereas before we didn't like necessarily have images and pre-images. We just had like two shapes and we said they were similar. Now we're talking about a transformation. We really want to get in the habit of putting image side over original side. If it's not a transformation, Jaden, you can do whatever order you want. But since we're talking about transformations, we want to do image over original. Okay? That'll be helpful for you if you can get that for those. All right, number 2. What similarities are there between reflections, translations, rotations, and dilations? So what are the similarities? Anyone want to raise your hand and tell me what are some similarities between those transformations?
120.
So anyone want to raise your hand and tell me what are some similarities between reflections, translations, rotations, and dilations? Yeah, Jason? Not sure? Okay.
Well, the dilations, they're like the same shape.
Okay, and what about reflections, translations, and rotations? Do they change shape?
No.
No, so both keep the same shape.
So I say it right.
Yeah, both. That's one answer. Yeah, both keep the same shape.
Oh, it's 300. Yeah.
Okay. Is there anything else similar between reflections, translations, rotations, and dilations, like they have in common? What else, Matt?
That end product, all three, I don't know what you said, all three vertices, not only vertices, but in the same way.
Okay. So they there's like kind of a change in position. Maybe we'll say too. Change in position. Okay. Change in a position. Okay, so there's a change in position that results. Sometimes, though, reflection, translation, and rotations, you can end up going back to the original, right? That was congruence, right? If you can, like, reflect, translate, or rotate from one to another, that can be congruence there. But yeah, okay, that normally results in a change of position. What about angles? What about angles in a dilation versus angles in a reflection, translation, rotation? What happens with the angles? They are the same, that's right. So angles stay the same in both reflections, translations, and rotations. Angles stay the same. Okay? All right, so I think that's pretty good, actually. What about differences? Differences. Okay. So what's that? The sides. That's right. Sides change length in dilations, but not in
So much stuff to write down.
reflections. I know. I'm going to abbreviate here. Reflections, rotations, and translations. Okay. So sides change length in dilations, but not in reflections, rotations, and translations. All right. All right. So questions on that? That's pretty key right there. Okay, that's a big concept, knowing that the differences and similarities between reflections, rotations, translations, and dilations. Right.
But not what? What is that mean?
But not in reflections. I abbreviated ref, rot, and trans for reflections, rotations, and translations.
Referee.
Referee. That's right. Okay. Can I turn the page there?
Yeah.
All right. So we're going to look here and try and actually dilate a line segment. All right, we're going to actually try and dilating here using our rulers and straight edges here. So it says here the dilation of a line segment, the pre-image, okay, so the pre-image is the original, right, is a line segment whose length is the product of the scale factor and the length of the pre-image. So if we were to dilate this by a certain scale factor, okay, remember the scale factor is like whether it gets bigger or smaller, that number that we're multiplying by, basically, okay, then the length of the original will be, the length of the image will be whatever that scale factor is times the length of the original. All right, so let's take a look at that here. So we're going to dilate this line segment by a factor of 3. The center is point O, and we're going to dilate it to a different segment there. Okay, so here's how we're going to do that. All right, you're going to take, and we only need a straight edge and a straight edge for this with a a ruler and stuff. So we're going to take O. Okay, and we're going to line up our rulers so that O goes through A like that, and we're going to draw a long kind of ray like this. Okay, we're going to draw a ray OA, and we're going to draw a ray OB, and then ray OC. And if this is too much, I'm going to end up tearing my page out because I can't do this. It's too much. Okay.
What page do we need?
Page 578 is what we're tearing out right now, just so we can get this done. So you're going to do ray OB.
Wait, what are we supposed to be connecting all this?
Yeah, we're doing a ray from O through A, a ray from O through B, and a ray from O through C. No, you want to draw them pretty long though, because we're going to be dilating here. So. Okay? So now, here's the key. We are going to be dilating by a factor of 3. So here, I'm going to show it. We're going to do it. Yeah, I'm going to show you how to do this. It's not that hard with your ruler. Okay? So let's measure from O to A, the distance from the dilation to the original. And from O to A looks to be about 1 centimeter exactly, and that's really nice. Okay? So if we're going to dilate by a scale factor of 3, Gabe, how far do I need to draw A prime away? If O to A is 1 centimeter, and I want to dilate by a factor of 3, how far away should A prime be? So, actually, I see what you're saying. Shh, listen up, please. Shh. We want it to be times 3 away. So 1 times 3 is 3 centimeters. So from O, we're going to measure from O, okay, along this ray to 3 centimeters, and then right there. Okay? So there's A prime. It is 3 centimeters. You can see right there. 3 centimeters away.
Why there?
So the point is that we want to take this original distance from O to A of 1 centimeter, and we want to then dilate it by a factor of 3, times 3, so we make it 3 centimeters away. No. It's 3 from point O. So originally we had a 1 centimeter from point O. Now we're going to go 3 centimeters from point O. Okay? It's 3 times longer. O to A is 1 centimeter. O to A prime is 3 centimeters. So it's 3 times longer.
Wait, how do you know what A prime is? Like,
you measure 3 centimeters.
Oh.
I measured 3 centimeters. Okay? So that we're good with that? O to A prime, 3 centimeters. Okay, now let's do O to B. So we have to measure from O to B. So let's see here. O to B, I get like it's 0.9 maybe? 0.9 centimeters? I would be very hesitant about doing that because when we start to like round and things, then we'll have some issues with the correctness of our dilation. So let's say it's 0.9, but look, we got our calculators handy. So 0.9 times 3. So I have to measure out 2.7.
Wait, why are you multiplying it?
Because we're dilating by a factor of 3, so we're going to multiply the distance times 3 times because it's a scale
Why
factor.
wouldn't you just put your ruler on it and mark 3?
What would it be?
2.7? Well, again, since I'm saying 0.9, I'm going to measure out 2.7 because that's 3 times as much. So, hold on a second. All right, so there's, and then 2.7, there's 0.5, 0.6, 0.7 right there. Okay, so there's B prime. Question there, Matt? Yes.
Why do you have to do OB when you can
That's true. You could do it that way. You could do it that way, yep. You could do it that way. I like to do them all just for now, Matt, because I want to make sure we're very thorough, but you're right. Well, that's okay. Yeah, Jade?
For A,
Yep.
what do you do? So, like, you make a point on the floor?
So, no, I measured from O. From O, I measured out 3 centimeters. Put a point. See, there's a 3 centimeter mark? Put a point. From O to A, prime, 3 centimeters. Okay? And then O to B was 0.9, so I went out 2.7 then. Put a point right there. There's B prime. And then O to C, let's measure that.
It's 1.4.
1.4? 1.4, thank you. 1.4 centimeters. So again, 1.4 times 3, 4.2. So we're going to measure from O out 4.2 centimeters. And then there's C prime. Okay, and then hopefully, if we do this correctly, it should all create one segment there. Okay, so this is our image right there. There's the image. I'm circling it just to make it more obvious because there's so many lines in there that I wanted to circle it just so you can see, like, that's the thing that we're trying to finally get, right? So, now let's see here. Okay, so there's A prime, B prime, C prime, right? We create that new segment. Does anyone see any relationships, for example, between the segment AC and A prime, C prime? Any relationship you can see there? They're straight line, okay. They are parallel, yes, okay. If we were to actually make this line A prime, C prime, make this a line, and make AC a line, right, other segments, if we made them lines, if we extended them forever, and we extend that one forever, they would never intersect. They are parallel, exactly right, okay. Jane, did you have something else? I'm sorry, what did you say?
Oh, no, I was going to say something linear.
Okay, so, I mean, they do make a straight line. They are collinear. A prime, B prime, C prime are collinear on the same line, just like A, B, C are on the same line. That's important, too. We don't want that to not happen. What about the lengths here? Let's take a look at the length. So from A to C, we could say that's roughly, I don't know, what would we say that? 1.6 maybe? Right? The length from A to C is 1.6. What do you predict then the length of A prime, C prime will be? Or how can we figure out the length of A prime, C prime without actually measuring it? What could we do here? Well, 1.6 times 3, exactly right, because our dilation is a scale factor of 3. So 1.6 times 3, we expect it to be about 4.8. Well, let's see here. It should be about 4.8.
Wait, where did you get 1.6 from?
It's definitely not. Okay, so hang on. All right, hang on a second. Let me check my measurements here. We measured from A to C. You know, I'm going to say maybe 1.7 there, because it does look, now that I'm measuring, it's maybe a little bit closer to 1.7. So let's try that, and gosh, I hope that's closer now. So I got 5.1. Is that better? Yeah, look at that. Okay, I was off a little bit in my measurements there. So about 1.7 is that measurement, and then look at that, 5.1. Okay, how about that? That's pretty nice.
How do you measure not a straight line?
Like a curved line or something like that?
Yeah, because like mine's like,
Oh, it's not exactly like straight?
yeah.
Yeah. So, again, because that's just errors with this. I would say just use your ruler and just kind of, I would measure from A prime to C prime, just use that and make that a straight, and then go from there. Okay? Okay.
It's like, I got like 5.5.
So, again, it's a matter of, how precise we are with our rulers and stuff like that. That's what the error is. But understand that it should be 3 times the length here, and then the distance shall be 3 times out and stuff like that. Okay. So let's go down here and reflect real quick. So number 3 says, make a conjecture about the length of the image of a 4 centimeter segment after a dilation with a scale factor of K. So here, right, we have a length AC, it was 1.7, I'm sorry that's so sloppy, but that was length of 1.7, and then A prime C prime was 3 times that, right, because its scale factor was 3, times 3 gives us the 5.1. So here, if our scale factor is K, and the original is 4, what can I do to that 4 to then give me what the new length should be? What should we do with that scale factor? Well, we could draw a 4 centimeter segment, but if we're dilating it by a scale factor of K, what can we just do mathematically to figure out what the new length should be? If our original is 4, not add them, multiply. So yeah, 4K would be the new length. Now here's a good question. Can the image ever be shorter than the pre-image? Could we dilate to get something smaller? Yes. What kind of scale factor would that need to be, though? Non-negative, actually. It wouldn't be negative to make it smaller. That's good thinking, though. It would be a decimal, a fraction, something between 0 and 1. It's like a scale factor of 1/2. So a scale factor between 0 and 1 would make the image smaller. Okay, a scale factor between 0 and 1 would make the image smaller. So, for example, like a scale factor of 1/2. A 1/2 scale factor would shrink the thing by 1/2. Okay. All right, questions on any of that? So 4K is the scale factor of the image, and then a scale factor between 0 and 1 would make the image smaller. Okay. So let's take a look then at the next page where we're going to, again, kind of analyze properties of a dilation. Okay, so yeah, I know some people are still finished writing there. So a scale factor between 0 and 1 would make the image smaller. All right. Okay, so we're going to look at then properties of dilations. You got it over there, Kyle?
Yeah.
Okay, properties of dilations, next page, okay? So, the center of dilation, so page 579, page 579, the center of dilation is the fixed point about which all the other points are transformed by a dilation. The ratio of the lengths of corresponding sides in the image and the pre-image is called the scale factor. So remember, scale factor is important. Scale factor, like I was telling to Jaden earlier, it's image over pre-image, always. Okay? Before, we didn't worry about how we set it up. Sometimes we did bigger over smaller, sometimes we did smaller over bigger.
Remember, I did that homework that you told me.
Okay. But now, when we're talking about transformations, dilations, it's always the image side over the pre-image, matching pre-image side. Okay, so don't forget that. That's important. Okay, properties of dilations. Dilations preserve angle measure. Duh, we knew that. Dilations preserve betweenness. So that means if you have a point between 2 points and you dilate it, that point will still be between the other 2 points. Collinearity. What does it mean to be collinear? To share the same line. Be on the same line. Okay? Right, planar, coplanar, exactly right. Dilations preserve orientation, so you don't change the order of things or of the where it's oriented. Dilations map a line segment to another line segment whose length is the product of the scale factor and the length of the pre-image. Right, that's what we just talked about. When you dilate a segment by a scale factor of 3, we multiply the original length by 3 to get the new length. Dilations map a line not passing through the center of dilation to a parallel line. That's what Julio pointed out, right? That when we dilate a line or dilate a segment, they are parallel. The dilations are parallel to each other. Okay? So, we can kind of look through here and see. Example 1 says, determine if the transformation on the coordinate plane is a dilation. If it is, give the scale factor. So if we look here, it preserves angle measure, it preserves betweenness, it preserves collinearity, points are still in the same order, but it does not preserve orientation, right? What type of transformation is being shown here? It's a reflection, not a dilation, okay? So it does not preserve orientation. Now let's look at this next one here for letter B. Does it? And I understand we're not going to go through and actually measure these just because it's going to be, we're going to get all different measurements and stuff. But if we look at it, does it look like it preserves angle measures here?
Yes.
Yeah, so we'll put a yes. Okay. Does it look like it preserves betweenness?
What is betweenness?
Again, it's just do points that were between A and B still look like they would be between A prime and B prime?
Yeah.
And so, yeah, it does preserve betweenness there. It's kind of hard to see here, Kate, because we don't actually have additional points. All we have are just the vertices and stuff. But, you won't have to worry too much about that property, really. Collinearity, does it look like points that were on the same line are still on the same line? So, yeah. Does it preserve orientation?
Yeah.
Yes, it does. A is still kind of in the bottom left here. A prime is as well. C is on top. C prime's on top. B is in the bottom right. B prime's still in the bottom right there. So, yes. Scale factor.
1, 2.
Yeah, it looks like it's 2, right? It gets twice as big.
Well, how did you figure that out?
That is hard to figure out here, I agree, because of the diagonal relationship. So how were you guys able to figure that out?
No, I just
You can just see it in your head? Same thing, Julio? So, let me show you one way you can kind of see it here, Ikeba. 1 second. So, okay, so, sorry, no, actually, go ahead. What'd you say there, Jason?
Just look at the smaller triangle and the bigger triangle.
Okay.
It says -2.
Like A has coordinates -2, -2, and what does A prime become? -4, -4. Twice as much. So there's your scale factor.
How come the scale factor in the first one was 1 and the 2 dots and 1?
Oh, that's the ratio. I don't know. For some reason, they wanted to write the ratio of the corresponding sides here. They didn't ask for that here. They just asked for the scale factor, which is, you could do a measurement on the side there, divide by measurement on the side. But you can also use what Jason just said, which is the change in the coordinates from the original to the image. It's twice as much, so you just times 2 is the scale factor.
The ratio of your song, though, would be 1 to 1.
It would be, it's always image over original, so it would be 2 to 1. It'd be, so right, yeah, 2 to 1, like that. Which you can, you can see it here, it's a fraction, 2 over 1, right? Is this transformation a dilation then? Yes!
So if there's no to any of those, if
Yep.
there's no to any of those, then it's not a dilation?
Exactly. Any of these fail, EK, any of them, not a dilation. Yep. Okay. Turn the page, okay? All right, so we're going to kind of quickly look through these your turns here, just because of time. Okay. So number 5, we want to determine if this transformation is a dilation. Okay, so let's look at number 5 and determine if this transformation is a dilation. Okay, so again, we can look and see here, does it preserve collinearity? Does it preserve betweenness? That's kind of hard to see. Is the orientation still the same? Yes. Orientation. So, like, for example, B and B prime are still kind of in the same position between the image and the original here. Like, B is on top in the original, B prime is still on top in the image. C is kind of like to the left there, C prime is still to the left, D is like bottom left, D prime is still bottom left, E is still bottom right, E prime is bottom right, A is to the farthest right, A prime is still farthest right. That kind of like thing. I know it's, for example here, EK, here's a non-example. Here's a bad example of it.
Well, how about like the one below that? That's
Oh.
not orientation, right?
Right, it would not be an orientation. Well, right, exactly, orientation is wrong. Yes. Yes. You gotta go, yeah, okay. So anyway, this is really important though here, okay? So the original, we really want to come up with that scale factor. Okay?
I thought physical therapy.
So, okay. So the scale factor here that we want to try and calculate that. Now it's hard to calculate scale factor sometimes. So, like for example, we have like all these diagonal lengths, but here we have a vertical length that we can find the measurement of there. So, for example, DC, what is its length? What is the length of DC here? Guys, listen up here, please. It is 2. Thank you. Exactly right. So, if DC has a length of 2, we want to find what D prime C prime's length is. What's D prime C prime's length? 3. And to write our scale factor, I have to do what over what here? 3 over 2, right. Image over original. Exactly right. So the scale factor is then 3 over the 2 there, which can simplify to 1.5 if you want to, or you can leave it as the fraction 3/2.
Why isn't it 2 over 3?
Because for scale factor, we always do the image on top over the original to give you the right factor
so the
here.
pre-image over the original?
The image over the pre-image, if you want to use the pre-image word. Image over pre-image. So 1.5 is our scale factor there. Okay, that's important. Does that 1.5 make sense? The image, is that bigger or smaller than the original?
What was the question?
Is the image bigger or smaller than the original?
Bigger.
Bigger. And our scale factor, is that bigger or smaller than 1? It's bigger than 1, so that makes sense that our image gets bigger there, right? Our image is bigger than the original. If it's smaller than 1, like between 0 and 1, it would shrink, it gets smaller.
But why won't?
Why does it get smaller? Because you're multiplying by...
No, not why. No, not like why gets smaller, but like why 1?
Oh, why? Because if it was 1, if you multiply something by 1, it stays the same, right? So that's the idea. Okay. We didn't quite get through everything, but I'm still going to give you guys an assignment here. So listen up, please.